Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 23, 2026, about 5 days ago. It proposes a distribution-aware improvement to finite scalar quantization that resolves the conflict between information efficiency and reconstruction fidelity, all with just a single line of code. The paper is titled iFSQ, Improving FSQ for Image Generation with One Line of Code. And as we'll see later, this simple fix allows for a unified benchmark that reveals a surprising sweet spot of 4 bits per dimension for image representations. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the core dilemma in quantization. In the red column, applying uniform bins to bell-shaped Gaussian data causes crowding in the center, which leaves outer bins empty and waste capacity. The blue column shows the alternative. Forcing equal usage makes the edge bins extremely wide, leading to large reconstruction errors. Finally, the green column demonstrates the proposed solution. By mapping the data to a uniform distribution first, the model achieves both perfect bin utilization and consistently low error, effectively solving the trade-off. So Figure 2 dives into the math to find that perfect mapping. The goal is to transform the model's natural bell-shaped outputs into a flat, uniform distribution. In panel A, the authors sweep a slope parameter, alpha. You can see the purple curve at alpha 1.0 is too peaked, while the yellow curve at 2.4 pushes too hard to the edges. The teal line at alpha 1.6, however, is nearly flat. Panel B confirms this, showing that error metrics hit their minimum exactly at 1.6, beating the standard hyperbolic tangent function located at 2.0. Table 1 validates these gains on a large diffusion model, DIT large. The top rows compare the baselines against the proposed method. Notice that the standard autoencoder, using 16 bits, gets a GFID score of 13.78. iFSQ, however, achieves a better score of 12.76, despite using only 4 bits, which is a massive jump in compression efficiency. The lower section breaks down performance by bit depth. We see a clear sweet spot at 4 bits where quality peaks. Going lower to 2 bits hurts performance, while adding more bits beyond 4 yields diminishing returns. So, Figure 4 leverages the unified iFSQ baseline to run a fair head-to-head race between autoregressive models in red and diffusion models in blue. In the pink region on the left, the autoregressive LlamaGen model takes an early lead, converging rapidly to a decent image quality with very little compute. But look at the crossover point, marked by the yellow star. Once we pass that threshold, the blue diffusion curve keeps descending to a superior final score, suggesting that while autoregressive models are efficient starters, diffusion models ultimately win on maximum quality. Wrapping up, this paper highlights how a single line of code can resolve the fundamental conflict between compression and fidelity. Beyond just a technical fix, iFSQ provides a unified platform that finally lets us fairly benchmark autoregressive versus diffusion models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.